Okay, so first we're going to solve this optimal transport problem exactly using an external package called POT, that stands for Python Optimal Transport. So you have first to install it, but on the Colab notebook, it's just the first line. And then you just import it using import OT, that is import optimal transport package. So we have this linear program that is, we minimize over all the transportation matrices, all the couplings P that have the right marginals, the sum of the Cij, Pij, that is the sum of how much it costs to transfer some mass from point I. Okay, so there's a zone here where I cannot speak. So Cij is the cost to go from point I to point J, and Pij is how much mass you actually transfer from I to J. And you want to minimize all the transportation matrices, and this is a linear program. So the first idea to solve it is to use Simplex algorithm, for example, and this is directly implemented into POT, into the package. So we're going to use some data, and so Marco used this analogy of the baguette and the restaurants in Paris. Here I propose that we use rather café and croissant. Okay, so you have some café that need some croissant to sell, that sell some croissant, so they have a demand that we know, and you have some bakeries actually producing the croissant. And we assume that the bakeries produce the exact same number, and the total amount of croissants that are produced is exactly the number of croissants that are needed by the cafe. And so this data is given to you by those lines. So we just load the data croissant, and X will be the matrix of the position of the bakeries. A will be the production of the bakeries. Y will be the position of the cafes, and B will be the production of the cafes. So in this whole afternoon, the first measure, the first weighted point cloud, we will always denote it by X with weights A, and the second one, the target one, will be Y with weights B. Okay, so that's just a notation here for the variables. And we can actually display those productions. So we see that we have 8 different bakeries and 5 cafes, and a total number of croissants being 441. And if we display the bakeries and the cafes, so a bakery and a cafe is just a point in R2, so if we display them, we get something like this. So let's say we're in Moscow, and we have those cafes in blue and bakeries in red, and the size of the points here is just proportional to the production of the bakeries and the demands of the cafe, right? So it's just our data. Sorry. So the first thing that you have to do is compute the cost matrix. We know that in optimal transport, what's important is, of course, the marginals, the histograms, that is here the productions and the demands of the cafe, but also the cost matrix. And here, what would be a good cost matrix? Well, we have the position of the cafe and the position of the bakeries, so maybe we can take the distance between the cafe and the bakeries. Or maybe we can take the distance squared, or maybe we could take something else, right? So here, let's say we just want to compute the L1 and L2 distance between the two. So this will give us 2 different cost matrices and 2 different solutions, and we'll see a bit like how the choice of the ground metric, that is a choice of how you compute the cost of transportation between a bakery and a cafe, will impact the solution, the optimal transport plan between the bakeries and the cafe. Okay? So could you load the data or not?
About the solution, because I will.
Okay. Okay, so once you load the data, you can just compute the cost matrix. So you can do this in a very inefficient way if you want. That is just like do a double loop and say for all I, for all j, blah, 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 I compute Cij equals the norm or the norm squared. Okay. And once you have this, you can compute the optimal plan using the function EMD, that stands for Earth Movers Distance, and then takes the following notation, that is the first two arguments of this function are the weights, that is here the productions and the demands of the bakeries and cafe, and then the third argument is the cost matrix that you've just computed. Okay. I don't know. Okay, so you do your double loop, you just compute the cost matrix between, that is the distance between the cafe and the bakeries, and then you just call this function ot.emd that will compute the optimal solution, that is the optimal transportation matrix. And once you have this matrix, you have to compute the cost. So the cost will be the scalar product, right, between the cost matrix and the transportation matrix, right? It will be the sum over all I and j of Cij, Pij. So you just have to compute the cost afterwards. Okay, so C1 and C2 are just the double loops of the distances, right? So you just take the norm between the position of the bakery number I and cafe number J, and then you take it squared in order to have C2. And then you just call this OT point EMD function that will compute the exact solution of the linear program. And this gives you those two matrices. So you see that there are some differences, right, into the two optimal transportation matrices. It means that depending on the cost, I mean, from an initial point of view, just saying, okay, I'm just going to take the distance or the square of the distance. You don't know. Maybe taking one or the other would be a good idea, but it gives a different solution into the optimization problem. Okay, so it means that when you want to model something using optimal transport, you have to choose carefully your cost because it will impact directly the solution and the value of the cost too. And now we can plot the bakeries and the cafe, and just by adding some line, okay, between the points between the bakeries and the cafe, a line each time you get some croissants that are transported from the bakery to the cafe, and the line has a width proportional to how many croissants are actually being transported between the bakery and the cafe. And so visually, we see what I was saying earlier is that depending on the cost, the transportation of the croissant is different. Okay. Are you okay with computing optimal transport exactly with the package? Okay, do you have any question for now? Okay, so now that we have computed the exact solution to this linear program, we can add the entropy to our problem. So we're not going to solve exactly, we changed the objective, we add this entropy term, and with a regularization strength that we will have to choose and tune in practice. So Marco told you about this entropy regularization and why we do it, because it's going to be faster in the algorithms, because from a statistical point of view it will be much more interesting, and also because in machine learning we want to avoid overfitting, and adding this entropy term will help against overfitting, right? So we have this term of entropy, and how do we solve this? How does this actually implies a much more efficient algorithm? Well, now we have this problem, this objective, and we have the constraints. So from an optimization point of view, what we're going to do is compute the, we have a constrained optimization problem. So we're just going to add some Lagrange multipliers. And with those Lagrange multipliers, for the different constraints, we're just going to get some optimality condition on the problem. And those optimality condition, if you rewrite them correctly, that's actually like 3 lines of computations, you get that the optimal transfer plan that is optimal for this entropy regularized problem should have a special form that is a diagonal matrix times a kernel k times a diagonal matrix. And this kernel k is just exponential of minus your cost divided by epsilon. So this kernel matrix we know, and we only have to know to compute the entries on the diagonal matrices. And those entries, how can we compute them? Well, we know that our optimal p star epsilon should verify the constraints, the marginal constraints. So for each I, the number of croissants that is going out of this bakery, number I, should equal the production of this bakery, right? So what we're going to do is we're just going to use those properties, those equalities, the marginal constraints on our solution. And this gives us a very simple iterative algorithm called Sinkhorn algorithm. And this algorithm is just a fixed point algorithm. Okay. So what I propose that we do now is actually implement this algorithm. It's 3 lines of code. So you should be able to do it. You just have to replace the formulas that I wrote in LaTeX into code, right? So first you have to compute this kernel matrix that has a closed form depending on the cost matrix and the regularization strength. And then we will alternate the projections, that is, we will alternate between computing the diagonal entries of the first diagonal matrix and of the second diagonal matrix. That is, this U becomes A over KV and V becomes B divided by K transpose U. Okay? And once we have coded this Sinkhorn algorithm, we'll show that on this same croissant and café application that we get a solution that is close enough to the optimal solution. Is there any question about Sinkhorn algorithm? Or is it too simple? Okay, so first we compute the cost matrix, the kernel matrix, sorry. That is just the exponential of minus the cost divided by epsilon. Epsilon is the regularization strength. And then we're gonna alternate the projection between u and v. So we have to be given a number of iterations. That is here just the parameter of the function. We first initialize the v, and then we're just going to compute the u. And then given the u, we're just going to update the v and do this again and again. Yes? Yeah, so you could take, here we just take the ones, but you could take something random, I think. Okay, so the question was how important is the initialization of v, that here I set to a vector of ones. So actually I think that you could start from any random v, okay, and it will still converge. So we alternate between those two projections, and then we just return the diagonal entry matrix with entries of u times this kernel matrix times the diagonal matrix with entries equal to v, diagonal entries equal to v. Okay, so it's actually very simple to code. It's like 3 lines of code, much faster than any algorithm to solve the exact solution to this linear program. And now we can compute this on our croissant café example. So here I took the L2 cost, and I just compute the plan. And there are 2 remarks. The first one is that you see that for the cost, I don't put C2, but C2 divided by the max. Or maybe you can take C2 divided by the median of C2. It's a bit of a hack, but why do you do that? Well, if you take the formula for Sincorn, then you have this first term that is the transportation term, right? And then you get the entropy that you add with a regularization strength epsilon. But this epsilon, it depends. How should you choose epsilon? Maybe you want to say, okay, I'm going to take 0.01, but it actually depends on the values of the cost. If the cost is very large, then you should take an epsilon that is very, very large. Otherwise, it will be almost negligible, right? So you have the entropy term and the transportation term should have be in comparable proportions, right? And that's why it's a good practice to actually divide the cost by the maximum or the median or some quantile of the cost matrix, for example. Especially when you work on real data that are very high dimensional, then the cost matrix usually becomes very, very large. And if you just say, okay, I don't do this, but I use an epsilon that is fixed and does not depend on the cost, it will be almost 0 because it will be, the epsilon will be really too small compared to the cost entries. Okay? And then the second thing is that we get some values that are not integers, we get something that is okay. So we have to transfer actually 1.75 croissant. So, okay, that's what am I going to do in practice? So depending on your application, if you have really to transfer the croissant, then here you don't really know how you're going to do it. But in machine learning, usually we don't really care if we have to split some croissant or not, right? But we see here that with an epsilon of the size 0.01, well, the transportation matrix that we get is comparable to the optimal one that we computed using a linear programming software solver, right? Okay, it's not 0, it's 1.75, but that's not too far. It's not 31, it's 29.67, but okay, that's good enough, right? For machine learning, for data science, it's good enough. So what you can do now is try to change the epsilon, and depending on the value of epsilon, plot the distance between the real optimal transport map and the map that you get. And you will see that if you take an epsilon that is closer and closer to 0, what you get is something that is closer and closer to the real optimal solution. So this is an experimental fact, but it's also well understood from a theoretical point of view. Yes? Sincorn.
Well, the function we just wrote.
Yeah.
That's computing the matrix exponential.
The matrix exponential.
Yeah, so it's computing np.x.
Yeah, so the kernel matrix is term by term. Right. It's not the exponential of the matrix, it's the matrix of the exponentials. But in Python, if you write np.x of the matrix, right, it's doing term by term. Okay, so for all the epsilons, what we're going to do is compute the optimal transfer plan for Sincorn and its optimal cost, just by calling this function Sincorn that we've just coded. And when we plot, what's going to happen is the following. So depending on the regularization strength, epsilon, the difference between the optimal solution of the entropy regularized problem and the optimal solution of the real transportation problem, the error will be smaller and smaller as epsilon goes to 0. And you can see this here on the plot. So this means that if you choose epsilon to be small enough, then what you get is really an approximation of your problem. But that was much simpler to code, and it's more vast, and it has all these good statistical good properties. Okay, and if you plot the same thing, but not in terms of the error of the solution, but in terms of the value of what you get, well, you see the same thing happening. If you take epsilon small enough, well, because you have the convergence of the optimal transport plan, obviously you have also the convergence of the cost. That is just a linear function into this optimal map, optimal coupling, right? So in practice, it's good enough. It has all those good properties, so that's what we're going to do always. And we'll see in the next part that in applications, it actually adds some real good properties. So it's not just a hack, as Marco said, it's also something that's very useful in on real data applications. And one last thing is this computational burden of the real linear program you want to solve. So here, let's say we take not like 8 and 5 bakeries and cafe, but 1,000 of them. And we just take them random. So X and Y on random points in 2 dimensions, and we're 1,000 of them. And we take just the uniform weights. Okay, so each one is just 1, to simplify. We compute this cost matrix, and we look at the running time of those things. So even if you use pod that is quite optimized to solve this linear problem, well, you see that here it's 120 milliseconds, whereas when you use our own implementation of Sincorn that was nowhere to be optimized, Well, you get 40 milliseconds, so that's a speed of 4 times. And that's only for 1,000 data points. So in practice, you may have much more than 1,000 data points. And what's good is that, well, for the exact LP solution, it really cannot go beyond a few thousands. So if you have 50,000 points, you're never going to actually compute this. But if you use Synchron, you can actually do it. And what's even nicer is that you can actually parallelize all those things on GPUs so that you get an even larger speed up. And you can go up to hundreds of thousands of points. So on real machine learning and data sciences applications, it will be very nice to actually be able to scale to that number of points. Now the last thing I wanted to talk about in this first part is optimal transport in dimension 1. So in dimension 1, we have this special property that the optimal transport coupling is actually given in a closed form. So you don't have to solve explicitly this linear program. You don't have to even approximate stuff using Synchron. You can actually compute it very quickly in an n-log n algorithm. Why? Because you just have to sort the points. So in one dimension, you have those points. So let's say here, to be very simple, 4 points, 4 blue and 4 red points with unit mass. And then we know by the theory that the optimal coupling will be just by sorting the points. Yes? Yes?
Actually, like the whole point to implement this Synchron is basically to make it faster, right?
Faster, but you also get better properties.
But in general, just like with this time, I just run these solutions in notebook, and it's kind of slower for me. I don't know why.
Okay, I don't know. But usually it's faster, and also you can parallelize stuff. And yes. Yeah, so optimal epsilon, it's actually a good question. So in practice, what you would do on real data, in order to tune the epsilon parameter, you may have to do cross-validation, for example. So you have an hyperparameter, and depending on what you're doing, you may have to cross-validate to compute something. Okay, so let's go back to this one-dimensional case. So in this one-dimensional case, we know by the theory that we just have to sort the points. So here, the optimal coupling will be, we know by theory, it should be the red, red 1 should be with 4 blue, 2 with 3, 3 to 1, and 3 to 2, right? We just get the leftmost red to the leftmost blue, etc., the second leftmost red to the second leftmost blue, and so forth. Okay, so what you can do is actually compute this using our 3 different algorithms. That is, you can compute this using the theory that tells you it's going to be a sort. You can compute this using this OT.EMD exact solution. And you can compute this using our Synchron algorithm. Okay, just to check that, sanity check, that, okay, theory tells us it's just a sort. Well, let's check it's actually a sort. And also you might ask, why are we interested in one dimension? I mean, in machine learning, we're not interested in one dimension points. We're just interested in high dimensional data, right? Well, so there's different reasons for this. One is that you can show that using one-dimensional projection of the points, you can get actually some good approximation of the Wasserstein distances. So one idea is say, okay, I've got all my points in a very high dimensional space. What I'm just going to do is I project everything on the line and compute the optimal transport on this line. And this is just a quick sort. So it's very easy to do. And now that I've done this on one line, I can do this on the second line, and on many, many lines. And if I take many, many lines, random, uniformly at random, I can compute many different values of the Wasserstein distances between the projected point clouds, right? And then you get all those distances and you average them. So you take the mean over all the directions of the Wasserstein distance on the lines. And that's very easy to compute because it's only doing several times a quicksort. So that's quick. And by doing this, you get actually something that has some meaning in applications. You can show that in real life applications, you get some, you can extract some geometrical information from only the one-dimensional projections of your data. So that's one reason. And the second reason why we're interested in one-dimensional optimal transport is related to what Marco is going to talk to you about tomorrow. Okay, so let's just do our sanity check. So we can compute the optimal plan that we know is the solution to the exact LP. Then we can compute the optimal plan according to Sinkorn. And we can compute this optimal plan given by theory, that is just a quicksort. Okay? And everything's fine. We find exactly the same thing that 3 times. Here, for Sinkorn, we get the same thing because we chose an epsilon that is very small and I rounded the solution, right? Otherwise, it would be 0.99 something. And finally, I just wanted to add something. If in Sinkorn, you try to take epsilon being very, very small, like 10 to the power minus 7 or something like that, it should not work. Why? Because everything is going to explode. In your kernel matrix, your kernel matrix is the exponential of minus the cost divided by the epsilon. But if epsilon is very, very small, then you're just computing the exponential of minus something that is very, very big. Okay? And so everything will collapse or blow up, and you won't see anything. So what you can do is compute everything in the log domain, okay, to stabilize everything. And in part, in this library, if you take ot.Sinkorn, it's just going to do Sinkorn, and you can use method equals Sinkorn stabilized that will stabilize the computations so that you can compute this even with a very, very small epsilon. Okay? So if you ever need to compute stuff with a small epsilon, you should use stabilized version of Sinkorn. And sometimes on real data, small epsilon is not that small, actually. So it could be useful in practice. So for this second part, we have 1 hour and a half. And what we're going to do is use the Wasserstein distances, that is the optimal transport distances, on real data applications. And we will see basically 2 applications. The first one, an application on images, and the second one, an application about text clustering. So because we have 1 hour and a half, what I'm going to do is first explain a bit the data and what's the goal of the application, the first application. And then I will let you just go through the notebook, and you can ask for help, of course. And I will correct, but I will give you time to actually code, okay? So from now on, we're not going to use our own version of Sinkorn algorithm. We're just going to use the one provided by the package pot, okay? And maybe we will use the stabilized version if needed. Okay, so the first application is about color transfer. So we're given 2 pictures. So one of a landscape and one of a portrait, both of them being pictures by Egon Schiele. And the goal of this is, given those two pictures, there is our data. We want to take one picture and give it the colors of the second picture, right? So we don't care about transferring the style of the painting. We don't care about, you know, just transferring the shape of the lines. We just care about transferring the colors. So we want to have these landscapes, but with the colors of the portraits, and the portraits with the colors of the landscape. So we want to transfer some colors, and because we're doing optimal transportation, okay, we want to transfer some colors, we want to transport some colors, so maybe there's some optimal transportation hidden behind. Why? Well, each picture is just an amount of pixels, and each pixel has one color, right? So if we don't care, if we only care about the colors and not about the style, not about the shape of the lines, not about the geometry of the pictures, if we just care about the colors, we can just forget completely about the structure of the image. So each image is just a list, now a list of colors without any order or any structure. So we just get a list of colors. But one color on a computer is just three numbers: how much red, how much green, and how much blue you get to form that color. So each pixel is one color, is three numbers, that is one vector in a three-dimensional space. So what we're going to do is say, okay, I got my two pictures, and I'm just going to transfer them to have 2 point clouds in 3 dimensions. Okay, each point will be one color of one picture. So we have 2 point clouds, each one for each in the color space, that is the 3-dimensional space of red, green, and blue. Okay, and now that we have those 2 point clouds, we can do optimal transportation between those 2 point clouds. Well, we need some weights, right? So we're just going to take uniform weights. I mean, we do not want to have some colors that are more important than others. So we're just going to say, okay, I'm going to take the uniform weight. And by doing that, we're just going to have 2 weighted point clouds. And now we can actually compute optimal transport. So we get a coupling. Let's say, okay, we computed this. We get a coupling. What am I going to do? Well, I have one color in the first image, let's say some red. And I want to say, okay, this red should be transferred to some new color, right? Should be transferred. So the first thing is that we get images that are three-dimensional in the sense that they have the width, the height, and then the 3 colors, channels. So we have to only have a 2-dimensional array, right? We have a list of points, so we just have to reshape all our images into vectors. So it's just a reshape, and then we're going to have to do the inverse transformation because in the end we'll get some vector and we want to get an image. Okay, so that's just a reshaping operation. Okay. And then the second thing is that I lied a little bit, right? So I told you, okay, you get those 2 color palettes, those 2 point clouds in the color space, and okay, I'm just going to compute the optimal transport coupling between the two. But we're not doing that. Why? Well, those images have hundreds of thousands of different colors. So what's going to happen is that we're going to get measures with a lot of different points. And because we're a bit limited on a single laptop, we cannot compute explicitly this thing, even with a synchron algorithm. Not using GPUs. So what we're going to do is quantize our measures, and that's something that Marco mentioned this morning, that sometimes you can just quantize a measure and do some stuff with this. So quantize your measure means that we're going to sum up our point clouds with a much smaller number of points on which we're going to be able to do some computations very fast and Okay, so in order to do this, we do k-means. So we're going to say, okay, take my point cloud, and I'm going to compute 1,000, let's say 1,000 centroids, just the 1,000 k-means, right? And now I take all the centroids, and I say, okay, those centroids, I take the empirical measure on those centroids, that is the uniform weights on those centroids, and this gives me a new probability measure, a new weighted point cloud that have only 1,000 different points, and that somehow, well, represents the colors of the images. And I'm going to do this for both images in order to deal with measures that have 1,000 points and not hundreds of thousands of points, which you could deal with, but not on my laptop. So in order to do this, we're going to compute the k-means, but using mini-batch k-means. Otherwise, it's going to be way too slow because we have way too many points. So we just do some mini-batch k-means, and this is the first quantization of this is the quantization of our measures. Okay. Yeah.
How do you fix the size of
This of samples, or
you are going to use mini-batch k-means. So how do you fix the size of patches since it impacts
of the batches?
it impacts the clustering?
Yeah. So the question is, how do you choose the size of the mini batches in the mini batch k-means? So I don't know. I mean, I think it's not really important. You just get some quite good quantization. Because you quantize your measure, you of course going to lose a lot of information, right, about your measure. So now if you're just going to take mini batches of size I don't know what or I don't know what, not going to make a huge difference in the end. Okay. But you can try several things, and if you find some very different results, just tell me. Okay, so we run this mini batch k-means, and now we can display our point clouds on which we're going to compute the optimal transport plan. So for the landscape and the portrait, we get those two different point clouds. There are the centroids, the 1,000 centroids, and that's our measures. And they quite well represent the colors of our two images. So we see, for example, in the portrait that there's a huge concentration around the beige colors, whereas for the landscape it's more in the black and blues, and it's a bit more diverse. So it seems, okay, quite fine. Okay. So now we have to compute the optimal transport plan between those two weighted point clouds. So weighted, the weights are just going to take uniform, so you just take the vectors of ones. Okay. And now we have to compute the cost. So as we said earlier, and we saw in the first part of this tutorial, well, choosing the cost will impact the solution of the optimal transport algorithm, the problem, right? So here I chose to take the squared norm, but maybe if you take norm or something else, or it may give different results in the end. So maybe here you see that we're dealing with colors. So maybe the squared Euclidean distance in this RGB space is not really the most appropriate. It's actually very simple to compute, but maybe we could come up with some specialist knowledge. So maybe you're a specialist of colors and you know that this color is more similar to that color, and you could design some specialist cost matrix, right? So that's how you can choose in practice. If you don't know, you usually take the squared Euclidean distance, but sometimes, you know, this distance has a real meaning, and so choosing a better distance could give better results in the end. Okay? But here, just let's stay with the squared Euclidean distance. Okay, so we can compute it. So you can do your double loop, so you can do some a bit more interesting, a bit faster methods, but you get this cost matrix. And now we're just going to compute the optimal transport between our two measures with our cost matrix. So if we want to solve the optimal, the exact linear program, we just have to call ot.emd. So the weights are just the vectors of ones, and the cost matrix is just the cost matrix that we've just computed. And this gives us the first optimal transport plan that we're going to look at. And then we're just going to compute for synchron using different regularization strength. So for reg in regs, so for the different regularization strength that we're going to look at, we just compute the synchron optimal transport plan, the entropy regularized, the solution to the entropy regularized problem by calling ot.synchron, again with weights being uniform, so all equal to ones, and the cost matrix that we've just computed, and the desired regularization strength. Okay? And we save all those plans in this list, OT plans. Okay? Now we want to transfer the colors. So for each color in my initial image, I have to for each color in my initial image, I have to find a new color. So how am I going to do that? Well, first I'm going to transfer the centroids. That's the thing where I know that I've computed yes. Sorry?
So the weights you initialize in both the EMG as well as the synchron algorithm.
Here.
Exactly.
Yes.
Can you just, I think you said something in the first tutorial, but I kind of missed it. Can you just, like, why do you choose these weights? It doesn't matter, you could choose anything, or?
Okay, so the question is about how do you choose the weights in optimal transport or in synchron. So the thing is, here we use the vector of ones because we want to get uniform weights. That is, we have different colors, and there's no a priori reason why we should give more weight or more importance to one color than another, right? But
Just rescaled automatically.
no, the colors. Not sure what. No, because you're not following, Marco. Yes. Yes, okay. Yeah, but it's one color. Okay. Okay, so
If I would
yes.
put weights which would, for instance, reflect the density of, say, points which are associated with one centrum, I would get a uniform color. Like I would destroy the color distribution in the picture. I could just make a essentially white noise if I wanted to.
Yeah, if you change the weights by random stuff, you could get, yes. Yes, that's a good thing. So what Marco is proposing, and that you should maybe implement, is instead of saying, okay, I'm going to give a 0.1 to each of the centroids, maybe we can say, oh, but there's some centroids that are more important than the others. The centroids that have more points in their cluster are more important in some sense. So you could get some weight that is proportional to the number of points in this cluster. And maybe I think that you would get better results, right? So that's a good remark. Thank you.
Sorry, you would get a
yes.
result, you say?
Yeah, I can imagine that you would get something. That, because the quantization would take into account the fact that there may be some colors that have more points, like maybe, yeah. 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 Okay. And actually, that's what we're going to do in the second application about text. So I think we can easily change it here. Okay, so now we want to transfer the colors, and we have our weighted point clouds with uniform or non-uniform weights, as you wish. And what we're going to do is first transfer the colors for the centroids. So we have this map, this transfer plan, and we say, okay, one centroid may be mapped to several other centroids, right? There may be some splitting. So what you do is you take one color, it is mapped to several other points, and you just take the barycenter of those points. And when you think about it, it's just taking a dot product between the optimal transfer plan and the centroids, right? Because you say, okay, my first point, my first centroid, number 1, it is mapped, let's say, half of it to number 2 and half of it number 3. So what you want is the mean between number 2 and number 3. So you just have to say, you just have to compute the dot product between the vector of 0, 0.5, 0.5, and then zeros, times the centroids of the second measure, of the target measure, right? So when you want to take the barycenter of the points where you're getting mapped to, you have to compute the mean of those points. But those points, they are the centroids of the second image, right? So the centroids of the second image, here it's k-means 2 dot clusters centers. So you get this. So those are the centroids of the second image. And now the first centroid of the first image. It's mapped to the thing according to the first line in the matrix OT plan, right? For your transfer plan, the first line tells you where your first point is getting mapped to, okay? And with weights, possibly with different weights, okay? So now if you take the dot product of this first line of your OT plan matrix, so that tells you with some weights where your first point of the first image is getting mapped to, and you take the dot product of this line with the centroids of the second image, it will take just the linear combination with the weights, with the according weights of the transfer plan, the barycenter of the centroids of the second image. Okay? Is this clear? Okay? You possibly don't have a map. You have a coupling, you have mass splitting. So I want to take the barycenter. And taking the barycenter is just taking a weighted mean. The weights are given by the transport plan, optimal transport plan, OT plan. And the thing that you want to weight is just given to you by the cluster centers of the second image. So k-means 2 dot cluster centers. Okay, and just take this dot product between the two, and that's just the weighted sum. That's the average. Okay? So this is a bit of a trick, because in practice you usually don't have a real map, you have a coupling, but if you want to get a map, then you can always do this, and from a coupling, you get an associated map by doing this trick, by just taking the average of where you get mapped to. Okay? And this is called the barycentric projection. Barycentric because you take the barycenters of where you get. Okay? And now we have this samples transformed variable that tells you how the centroids have been transformed. That's the transformation of the centroids. But we're not really interested in the transformation of the centroids themselves, right? We're interested in the transformation of all the pixels of the original image, not the centroids. So what we're going to do is for each pixel in the first image, each color in the first original image, we're going to say, okay, this picture is mapped to this is in this cluster. I take the centroid of this particular cluster, I see where it is mapped to, and this gives me where the transformation of my color. Okay? So for each image, I look at its cluster, and I now have a transformation for this centroid that is given to me by this samples transformed variable. Okay? So what we do is we take the labels of the first k-means, that is the labels of the pixel of the original image that we want to actually transform, and we transfer them according to this samples transformed, that is the transformation of the centroids. And this gives us a vector of transformed pixels on the whole images, for all the pixels of the original image. And we only have to reshape everything so that it's not a vector, but it looks like an image. Okay? And that's what we do using this matrix to image function that it's just a reshape that we coded in the first place. Okay? So for each pixel, I see its centroid. I know its transformation using the RT map, and that gives me a transformation for all the pixels. Okay? So there's one thing with this quantization, is that the number of different colors that you get is equal to the number of centroids, right? So you lost a lot of diversity in the colors. But that's a price that we have to pay for this quantization. And again, if you have more computational power, you could compute this with more centroids or without centroids at all. Okay, any questions? Yeah.
Can you elaborate a little bit on the adaptive class function? Because L2 norm doesn't work. So
okay. Yeah, so the question is, can I elaborate about the choice of the cost function, and because it does not seem to work in practice. So, so yeah, let's see a bit the kind of results that we get. Well, in this case, it's not too bad from the landscape with the colors of the portrait. But if we do it the other way around, we see that, well, there's a lot of irregularity, right, in the transferred images. So yeah, one first thing you could do is change the cost matrix, and maybe with something more intelligent, taking into account the colors. Maybe you should design a distance between the colors that takes into account how the human eye actually perceives the differences of colors and nuances and etc. So maybe this would improve stuff. But also it means that directly using optimal transport in this case is not very satisfactory. But what we see is first that when you add entropy, you get something that's a bit better. It's less irregular because basically we added some noise on the, we blurred a little bit this optimal transport plan. Sorry. So, so what we get is something that is less irregular. And you can think of it if you take the regularization strength to go to infinity. Okay, so in this case, what you would get is the completely, each color is mapped to all the other colors. And because then you take the mean, the barycenter, this barycenter projection, right? Then you just, all the colors are going to be mapped to the center of mass of the target image. So you're just going to get one color. So it means that when you add the entropy, what you, by blurring a little bit the optimal transport plan, what you're going to get is more regularity and less diversity in the colors, and that's what you can see here. Of course, the price that you pay for that is that you're less faithful to the real color palette that you wanted to mimic, right? If you take the regularization strength to be 0.1, yeah, your image is not irregular, it's better, but you completely lost the fact that in the target image, you had some very strong colors like vivid red, blue, or green, etc. Right? So you forget a bit, so you lost this information. So there is a trade-off between how much faithful you want to be to your target image and the regularity in this case. Of course, you can add other penalization. You can do other things, not more than entropic regularization, and you would get some other results. But, so there are different algorithms. Okay. Any other questions? No? Okay, so what we can do is go to the next application that will be about text and document clustering. So it's a very, very small and a bit stupid example, but it will show that Wasserstein distances have a interest in themselves. So in the first application, we were actually interested in the plan, in the optimal transport plan. The actual value, we don't care, right? We didn't care about what's the optimal value of the cost, right? We're just interested in the plan, in the displacement. So that's one type of application, but most often we're more interested in the actual value of the cost and less in the optimal transport plan itself. And that will be the case in document clustering. So we have some data. We have 7 documents in this case. We could have taken more. So 7 documents that are just scenarios of films. So there are different films like Kill Bill or Interstellar and some other movies. And we took the scenarios. A scenario is basically just words. And as a first approximation, we can just forget about the order of the words. Okay? So just now an unordered list of words. Now, okay, it's an unordered list of words, so it's kind of a point cloud, right? So we have to define some weights. So we could take some uniform weights, but maybe there's something a bit more clever. That is, the weights can be proportional to the frequency of a word. So if a word is very, very frequent in a text, it means that this word really means something in this text. So we should give more mass to this word, right? So we're just going to take non-uniform weights, but weights that are proportional to the frequency of the words. So now we have a point cloud, we have weights, everything's fine, but we can actually compute the Wasserstein distance. Yeah, but we have to have some notion of cost matrix, right? So we have to define what is the distance between one point and one other point. But our point here are words, so we have to find some good notion of distance between words. And in machine learning, what people usually do is some kind of embedding. That is, each word will be represented by a, let's say, 300-dimensional vector. And now we're just going to take the Euclidean distance, or the squared Euclidean distance between those vectors. So, and that's called basically word to vectors. So each word will be represented by a vector, and now the distance between two words will be just the squared Euclidean distance between the two vectors representing those words. And word to vec just create some embedding, some vectors representing the words that has some meaningful some meaning. Okay, so if two words have a similar meaning, they should be close in Euclidean distance, for example. So it quite makes sense to do that. Okay, so we have our documents. We have a list of words. There is now a list of vectors. So it's an actual point cloud in a 300-dimensional space. And we have our weights. That is just the frequencies of the words in the different documents. So each document is just a weighted point cloud. Yes?
Sorry, Simplex, and I missed it. You get rid of the first 2,000 words, which is a lot, because a normal stop word list is like 30 words. Why is it so many?
Yeah, so the question is, why do I get rid of the first 2,000 most common words, which is maybe a lot? Yeah, so I pre-processed those data, and in order to discriminate more the documents, you don't want words that are really too frequent, because they're not going to allow you to discriminate between the words. So I took between the documents, right? If you have very like the word to speak or to be, etc., that are very frequent in English, well, they're not going to allow you to discriminate between the documents. So just get rid of them. Maybe 2,000 is too much, maybe 500 would have done the job. I just do 1,000 anyway. And also, I got rid of the words that are very less frequent, because it can happen that you have one special word in some document that will completely discriminate this film. Like in Kill Bill, you had, for example, the word Beatrix, that is a character name, and that only appears in the second volume of Kill Bill. And because you have this special words that distinguishes this special document from all the others, it's completely not interesting to have those kind of words. Okay, but that's just kind of pre-processing. So we have our weighted point clouds in 300 dimensions. And what we're going to do is, for each pair of document, compute the optimal transport distance between the two. So the cost, we don't really care about the map, about the coupling. We're just interested in the cost. So we're just going to compute this using Synchron. We could use the exact optimal transport, but here we have many different words first, and so it's going to take a long time to compute. And second, we know that, okay, in machine learning, using Synchron and adding the entropy is quite a good habit to have. So from both a machine learning really point of view and from the computational point of view, it will be interesting to use Synchron. Okay, so I did all the data and pre-processing for you. And so what you get is just weighted point clouds, and you just have to compute the Wasserstein distances between all the documents. And we will see that this distance between this will give us a distance between the document, or at least a notion of similarity or dissimilarity between the documents that we can use to do some clustering of the documents, for example. Okay? Any questions? So the question is, do people use embeddings for images? I don't know. Maybe. Probably. Yes, they do. Yeah. So they do. Yeah. Like what you can do is, for some images, you can just take the value in a deep neural. You take one layer of a deep neural net, and you just extract those features, and it can be in this kind of clustering for images, for example, it would make sense. Exactly. Yeah, good remark. Okay, so let's get back to our document clustering. So for any pair of text, of documents, of scenarios, of films, we will have to compute the optimal transport plan between the two, or at least the entropy regularized version of it. So first we have to compute the cost matrix. So first we set a regularization strength. So here it's 0.1. You can try something else and see. You can look at the how it impacts the distances. If you take the regularization to be very small or very big, what happens? Just, you can look at it. And then we have to define the cost matrix between text I and j. So here I just coded a small function to do this. So in x we just get the points in x, and y the points of text j. And now we're just computing the squared Euclidean distance between the two. And in order to do this, this is not optimal, but instead of doing a double loop, you can just a bit vectorize everything. It's not, you could get rid of some diagonals here, probably, but yeah, it works. So it's just like computing the cost matrix between the embeddings, the point clouds in the 300-dimensional space. And then we're just going to compute the optimal transport distances between any pair of documents. So what we do is, well, we just compute the cost matrix with the function that we've just coded. Then we just get the weights. So the weights A and B are just the proportional to the frequencies of the words in the texts. Okay. And then we just compute the optimal plan using Sinkhorn algorithm with our regularization strength. And now, in order to get the value of the cost, we just compute the scalar product between the cost matrix C and the computed optimal transport plan. Okay? And we just store it. And we do this for all pair of movies. And now we can display for each, so we can actually display the matrix, and we can, for each movie, display the movie that is the most similar to it. So for example, here for Gravity we have Interstellar, for Kill Bill 1 we have Kill Bill 2, for Kill Bill 2 we have Kill Bill 1, etc. So it seems that we get some nice distance between the scenarios and the movies. So what we're similar in which way? Well, we basically similar words that have similar embeddings are going to be matched together. So what we're actually comparing is like the semantic similarity between the documents. So that's quite a nice thing to compare. Okay, and it seems to quite work. And in order to show this visually, this clustering, we can do just a multi-dimensional scaling projection in 2D. So we have this 7 by 7 distance matrix, right? And we're just gonna embed this distance matrix in 2 dimensions using multi-dimensional scaling. And by doing so, what we get is something like that. So we see that the 2 Kill Bills are basically almost matched together. So really we get the fact that those 2 movies are very similar. Basically they're the same movie, right? Then we get those Interstellar, Gravity, and The Martian movies. That is the sci-fi movies that share the same kind of words, the sci-fi words, maybe probes, planets, space, gravity, etc. And then we have those 2 blue words that I matched together, Titanic and Dunkirk. They're a bit, maybe they're not really matched together, it's not very clear. But maybe they're together because they talk about the sea, the ocean, the boats, etc., ships. Okay, and so we see that by computing the optimal transport distance between 2 documents, we can get some distance between documents that has some semantic meaning. Okay, and then we can use this distance in another pipeline, like clustering, but we could use it to other stuff if we want. Also, this is a distance between documents, but we could have used this as a distance between very small documents that is just sentences. So it just gives you a distance between sentences, for example, okay? So are there any questions on this or on the previous color transfer application? So of course, those two applications, they're not state-of-the-art. We did very simple stuff, maybe very naive stuff, but it's just to show you that we can very easily use optimal transport to design very quickly in a few lines of code some nice applications on real data, images, texts, etc. Okay. And the only external thing that we use is the Syncorn algorithm in this package, but we actually can code it in like 3 lines of code that we did in the first part. So you see, it's something that we can really code from scratch in a very efficient way. And then if you are really in the applications, you can do more intelligent stuff. You can design a real cost matrix that will be more interesting. You can tune the weights, you can tune the regularization strength in Syncorn algorithm. You can add some other kind of regularization. You can do a lot of stuff, okay? But that's basically very simple stuff that we can do, and that seems to work.
I have a question.
Yes, where are you?
Here.
Here. Yes.
Why did we dot with a matrix of ones in the beginning?
What we don't?
We dotted the matrices with a matrix of ones.
Where?
There.
Here? Here?
Yeah.
Oh, here. This thing here?
At the line below.
This.
Yeah.
Yeah.
Why?
So,
yeah.
Yeah. So basically, here you could do your double loop stuff, but it's not efficient. This is a bit more efficient. It's not the most efficient. But what you say is, okay, I'm just computing the squared Euclidean distance. So by just decomposing this, developing the thing, you have the square root of x plus y squared minus 2x dot product with y. And that's what I call xx, yy, and xy. And then understanding the line for xx and yy is just like really doing the simple line of computation to show that this is diagonal matrix with entries being the squared norms of xi's. And probably you can do more efficient without that many diagonal stuff, but okay. But that's still much more efficient than doing your double loop. Yeah, so if there is no other question, thank you very much. And I hope that you will think about optimal transport when you design your new application. And yeah, thank you for your attention.